So today's webinar is about managing large data sets. Well, in HPC and beyond HPC, it doesn't really have to be numerical, simulation data, but mostly it's about managing large data sets. So one of the common problems when you run large numerical simulations is that they produce a lot of data. They produce, gigabytes and gigabytes, terabytes of data, and it's really a challenge to write all this data from the simulation code because it's a bottleneck. So usually, if you try to, let's say, you're running fluid dynamic simulation, and you try to store everything or all variables at every time step, that will just completely dominate your pipeline, your workflow. You'll be spending 99% of the time not computing, but writing the results. And similarly, analyzing the results and store these files long term is also a problem. So people use all sorts of solutions to mitigate this problem. One of them is, instead of storing all variables, you can store just a selection of variables. Instead of storing every single time step, you can store every 10th or every 100th time step, right? So that results in much less data. So a newer solution, more complex but very elegant solution, is to do visualization in situ. So this is one of the topics I'm going to be talking about today. So in situ refers to using visualization libraries right from your simulation code. And when you talk about storage, long-term storage, there are lots of techniques you can use. So you can compress your data, and today I'll also be talking about lossy compression. You can store data using a distributed approach on a variety of different drives and file systems, using things like Git Annex, Git LFS, and so on. And you can use modern archival tools. So these are the 4 topics that are highlighted here. And all of these topics I gave longer presentations on before, so there are links to the recordings at the bottom of the slide. Today, because I have only 10 or maybe 12 minutes per each tool on average, I won't go into demos, into a lot of details. But if you're interested, just check out those webinars, and all of them have a lot of demos. So let's just jump in. The first topic I'm going to cover is data compression, and I'll be talking about lossy data compression. So to start off, lossless data compression we're all familiar with. You will always compress audio and video. We consume media. All this media is compressed, right? So that is, well, it's compressed by lossy compression. But when I talk about data compression, usually we are we're more familiar with things like gzip, bzip. So lossless data compression, where you have a file, a large data file, and can simply run a gzip utility on it, and it will compress these data file. So usually, on average, for typical 2-dimensional, 3-dimensional data set, typical lossless compression utility will not compress it much. So that really depends on the data. So typically it will compress it by, I don't know, 40, maybe 30, 50%, something like this. So sometimes you might have a data set that can compress quite a lot. But that's more of an exception. So here is an example in the figure. It's a 3-dimensional data set of a mantobulb, which is stored as an etcdf file. So it's an 800 cube data set, volumetric data sets on an 800 cube Cartesian mesh. And so if you calculate 800 cube in single precision, that will be almost 2 GB large. But because this data has a lot of redundant values, so essentially here what I'm storing is not so much a volumetric data set, but I'm interested in this surface. So it's the surface that produces this 3-dimensional fractal when you visualize it. But the values of the scale of the 3-dimensional scalar field on the outside of the surface and inside the surface are actually pretty much uniform. So because there's a lot of redundancy in this data, it compresses really, really well. So if you store this data set in single precision as an etcdf file, using lossless compression at 800 cube, then the file is only 12 megabytes large, right? But this is kind of an exception. So usually your data does not compress that well. And effectively, if you want to see how well you compress your data, how efficiently you store data set, well, you can just run a bzip or a gzip utility on it, and it's kind of a litmus test for testing the efficiency of your compression, right? So if your data set compresses by a factor of 10, well, that just means that you're not storing your data very efficiently, right? But anyway, so so lossless compression usually for typical output of numerical simulations does not give you much, maybe 30, 40, 50%. So enter lossy compression. So lossy compression, as I said, we are familiar with lossy compression when we consume audio files, video files. All of these were compressed with various lossy codecs. So lossy compression could be as simple as as changing the resolution or precision of your data. Let's say you have a 1,000-cube data set. Well, you can just do it at, I don't know, at 100-cube precision, right? So of course you lose a lot of data, but that way you can still, capture the main features of the data set and store it in a much smaller file. Or you can change the precision. So instead of storing, everything in, let's say, double precision or single precision, you can use special libraries that let you store in, I don't know, in 1/2 or 1/4 of the precision, and that gives you much less data, so much more proximate description of the data, but it gives you, 1/2 or 1/4 of the file size. So today I'm going to talk about two lossy compression algorithms. One is a library called ZFP, a very popular library, but not a lot of people in the scientific community know about it because it's you have to actively search for it. So that's one of the goals of this webinar, is to tell you about all these tools. And the other one is topological compression. So ZFP is based on orthogonal transformation based algorithm. So think of discrete cosine transforms, right? So you have all these coefficients, and then you just throw some of the coefficients that you don't want to keep. And topological compression is more difficult. So I'll have 1 or 2 slides on topological compression as well. So if you're interested in the details, then check out the webinars that I linked from the previous page. So both of these, both ZFP and topological compression, can reliably achieve a factor of 20 or 30 compression without actually any visible data degradation at all. And you can certainly go, so depending on what exactly you're storing, so for some data sets, you can achieve much higher compression up to a factor of 200 without losing too much data. But of course, really, how much you compress it really depends on what kind of data you're storing and what exactly you're after. So what kind of, small details you're willing to erase. And these algorithms work not on files, but on multidimensional, well, one-dimensional, two-dimensional, three-dimensional scalar fields. And compression artifacts in both of these, in both approaches, so in ZFP and in topological compression, show in very different ways. And so that means that you can actually combine both on the same data set. And there's a website that I think I have linked somewhere further down the slides that tells you exactly how to do this. In principle, you should be able to apply these techniques to other data than just a regular multidimensional field on a Cartesian mesh. So, for example, molecular dynamic trajectories or AMR data sets. How to do that in detail? Well, you really have to work out details yourself, or if you're interested, let me know, and I can certainly help you. But yeah, so originally they were designed for storing multidimensional scalar fields. ZFP or ZFP library was developed a number of years ago at Lawrence Livermore National Lab. It's completely open source. You can download the source at GitHub. It supports both lossless and lossy compression. Documentation is really, really good. So originally it was written as a C and C++ library. Now there are bindings in other languages as well, so including Python and Julia and a few others. So it's supported by a number of, so it's built into a number of projects, so 60+ projects that have this ZFP library built in. And let's just go to an example. So one thing that I want to say, they also mentioned that so throughputs are, so when you're compressing and uncompressing your data, the reported throughputs up to 2 gigabytes per CPU core. And then you have to doing this, if you're doing this on a GPU, then up to 800 gigabytes per second aggregate throughput. So the details of the algorithm are described in the documentation, really, really good documentation. And so as I mentioned, it relies on orthogonal transforms, so similar to trigonometric transforms. And the idea is that you calculate the coefficients of these transforms, and then you sort them in the order of decreasing importance, and then you truncate the stream in one of 3 ways. So there is a fixed rate mode, which is a floating, so you specify a single parameter, you specify floating number. So essentially it's a fixed number of bits per floating number, and it could be non-integer. So for example, 3.5 bits per each floating number that you want to store. There is the fixed precision mode, which is controlled by an integer parameter specifying the number of bit planes per transform coefficient. So this one I've never used, but it's described in the documentation as well. And there's also the fixed accuracy mode, where you can simply have a single parameter, which is the maximum pointwise tolerance or error that you're willing to apply to your data. So let's go to an example. Here I have a very simple example where I have a one-dimensional data set, which is just so initialized in Python with NumPy, so it's just in a range of integer numbers from 1 to 100. And here I'm plotting these as, so on the vertical axis, I have the data. And then on the horizontal axis, I have the index. So if the data is not compressed, then you have the red line, right, which is exactly what it should be. So each data value is equal to its index. So here I'm showing how to compress this first using lossless compression. So with lossless compression, you just pass it through compress underscore numpy function in ZFP library. And then when you uncompress it and you compare the two arrays, so the initial and the decompressed arrays, you see that they are exactly the same as they should with any lossless compression, sorry. So now with the lossy compression, what I do here, I specify the rate, the number of bits that I want to use to store every floating number. So each one of these data sets is a floating number, right? So it's actually double precision, oh, sorry, single precision. So it's single precision floating number. And then I compress it using the rate of, let's say, rate of 3.5. So I compress it, store it in this array, and then I decompress it, and then optionally I can print the number of bytes that I use to store that string. So and here I'm also showing how you can store these compressed array inside a file. So very easy. There is no common extension for ZFP compression. So I just use here ZFP just to to show that this is ZFP file, but there's no common suffix for this. So for this problem, let's see what happens. So if we start with a rate of 3.5, so that's 3.5 bits per floating number, then as you can see, the data is compressed very badly. So there are a lot of errors. But as you increase the compression rate, the numbers get better and better. And starting with a rate of 7.375, you actually get the result which is undistinguishable from the source. So this number, 7.4 bits per floating number, is less than a single precision, right? So in a single precision, you typically have 8 bits per number. So we have the original double precision data, and then we stored it down to roughly 7 bits per floating number. So that's not such a high ratio, right? But actually, for for bigger data sets, so for real live data sets, you have a much higher ratio because there you have a lot more data. So here's an example. It's a function that I use very often for teaching visualization and scientific file formats. And it's just a mathematical function defined inside a unit cube, right? So X, Y, and Z go from 0 to 1. So here I discretize these on a 300 cube mesh, Cartesian mesh. So 300 cube Cartesian mesh in double precision results in a file which is 206 megabytes large. So if you apply the usual lossless compression algorithms to it, for example, you compress it with a gzip, the file size goes down to 125 megabytes. So with a bzip2 goes down to 119 megabytes. So in netcdf, there's also lossless compression built in. So netcdf supports things like zlib or zlib library. And so if you enable it, then your file size is going to go down by roughly 20% to 159 megabytes. There's also lossy compression that netcdf supports. So there you can specify the number of digits that you want to keep. And if you use very aggressive compression, you can compress this file to 33 megabytes, but it's still not a lot. So it's a factor of 3 or so. So let's see what ZFP can do for this data set. So here I read the data set, read the netcdf file, I compress it in Python, and I try the rates of 2.0, 1.0, and 0.5. So much high compression ratio. And here I just store the compressed file with the .zfp extension. And here on the right, I just show as an example how you can read that compressed file, and then how you can decompress it and then convert it back into a regular netcdf file. So with this compression ratio of 1.5 a bit per floating number, this is what you get when I visualize this data set. So as you can see, with a compression ratio of 32, when I use 2 bits per floating number, I actually don't have any artifacts at all. So it's easy to see artifacts when you do contour maps. So in this case, as I increase the compression ratio, so you see that artifacts start showing, well, very barely when I use 64 times compression, and then with 127 times compression, so half a bit per floating number, things start to disintegrate. But here the point is that for this particular data set, you can use a compression of a factor of roughly 100 before you can actually start seeing any artifacts from compression, which is really impressive. So your file size went down from 200 megabytes down to around 3 or 2 megabytes. And so that way you're storing data a lot more efficiently. So topological compression is, I know just one implementation, and it's, so the idea is that essentially, if you're looking at a function, so here we have a two-dimensional function, but it works for 3D functions as well. So if you have a two-dimensional function that has a lot of oscillations, so a lot of local minima and minima, a lot of local, minima and maxima, then you can apply what is called a topological simplification to it. So essentially, you are erasing these small oscillations and replacing them with constant values. And then you apply some other processing to this algorithm, and that can result in a much smaller file size. So in this algorithm, there are two parameters. One is persistent tolerance. So basically, the maximum size, the size of these oscillations below which you erase all data. And then there is also the user specified error. And so having two parameters is better than having one parameter like in ZFP, simply because it lets you, to tune your compression algorithm to better compress your data specifically. So when you apply this compression algorithm to, it's much slower, I should say. So here's a data set which is it comes from a IEEE scientific visualization contest back in 2018. It's a deep water asteroid deep water impact data set when asteroid is coming from the upper left and hits the ocean. So it's a parametric simulation of this event. And here I just extracted a single variable from this data set, and I stored it as double precision. So I think, yeah, it's the sound speed that I stored as a double precision variable in a VTK file at 500 cube resolution. So that resolution, double precision, means that the file is 950 megabytes large. So here I visualize the file, and that's what it looks like. So, and then I apply, so if you try to apply lossless compression, you see that you don't really get a lot. So you get a maximum factor of a few. So if you compress it with topological compression, then so here are two parameters that I use. And in this case, I use the C++ VTK interface. And then you can see that the file compresses pretty well. So here I compress it down to 9.6 megabytes, which is a factor of 100 compression. And as you can see, there are barely any artifacts in this case, right? So for more complex data sets, compression works really, really well. So a factor of 100 compression, and you get almost no artifacts from compression. So let's talk about in-situ visualization. So in-situ, as I mentioned, is the idea of, so you change your simulation code to call visualization libraries right during simulation. So instead of storing your data, you are trying to use a third-party visualization library to either output much smaller data sets. So let's say if you're running three-dimensional simulation and you're interested in isosurfaces, so instead of storing the full three-dimensional data set, you can just store, the data that is needed for visualizing two-dimensional polygonal isosurfaces. And so alternatively, you can store simulations, images directly from the simulation code. So in both cases, instead of storing the original large three-dimensional data set, you are writing into much smaller files. And so this idea is referred often, it's called in-situ visualization, or often called co-processing. So you might say, well, wait a second. So we've been doing this for a very long time. So, 40, 50 years ago, let's say back in the early 1980s, when you were running numerical simulations, you would often, from Fortran or from, I don't know, BASIC or from Pascal, you would call an external visualization library, and these things existed, 45 years ago. And you would just, instead of storing two-dimensional, three-dimensional arrays on disk, you would dump these much smaller images. So there is nothing new here. Well, so let me rephrase the idea of in-situ visualization. So with in-situ visualization, what you're doing is you're using a specially created, specially designed in situ visualization libraries. So there are two good examples. One is ParaView Catalyst, the one I'm going to talk about today. There is also Visit LibSim, and there are a few other libraries that I'll mention in a few minutes. So the idea is that you are exposing your runtime in memory simulation data, so most notably runtime in memory arrays, so three-dimensional arrays, to the visualization library. And then you're using familiar interactive Python pipelines. So, and these pipelines you would typically create from a GUI visualization work. So you load your data set in ParaView, you visualize your data set, you store the script, and then you run the script as an argument that you pass to the simulation code, right? So you instrument your simulation code only once to expose your arrays to the library, and then you compile it, and then you can modify and run your analysis and visualization pipelines without recompiling your code, right? So it's very, very important that you actually don't have any visualization primitives inside the code. They're sitting separately in a Python script that you can modify and create totally separately from your simulation code. I'll be talking about ParaView Catalyst library, and originally it was released back in 2012, and the original release actually was not very convenient, I should say, for end users, simply because it relied on users mapping their simulation data, their in-memory arrays at runtime to VDK data structures. And this is quite hard to do because very often, your data is very different from what you would easily code inside a VDK object. And so you would have to map your data into VDK formats. And that way, it's actually very easy to make mistakes and to duplicate data arrays in memory, right? And that way, the memory footprint of your simulation code just balloons. In 2020, 5 years ago, Catalyst 2 was released, and it addressed that shortcoming. So they switched to a different data description of what is called Conduit API, and there is a website link here that tells you exactly how to do it in simulation code. But the basic idea is that essentially you pass a number of strings to the Catalyst library, strings containing data description that tell you exactly tell Catalyst how this data is structured, and it's really fairly easy to do. So when you start with this, you need two things. You need the Catalyst core API. So basically, you have to download the source code for Catalyst and then compile it on the machine on which you're going to run simulations. And then you need the ParaView Catalyst API. So essentially, a bunch of Catalyst functions from ParaView installation. And it is possible to use a precompiled version of ParaView, but I ran into problems, and I see a lot of people online had similar issues. I strongly advise to recompile ParaView from source, and I can certainly help you offline to do this if you're interested in this. So the idea is the following. So you download and compile the core Catalyst library. Then you download and compile ParaView, the ParaView server, and you enable ParaView, you enable Catalyst in ParaView, right, when you configure ParaView. And then you start with examples. So there are pretty good examples in the ParaView source code. So in ParaView, not the most recent version of ParaView, so the latest one is 5.13. I noticed that they changed some things in Catalyst going from 5.12 to 5.13, so that's why I show 5.12 here. And in ParaView source code, you go to the examples Catalyst 2 subdirectory, and there are some good examples. I wrote my own examples that I showed in the webinar when I gave the webinar on Catalyst 2.5 years ago. And I have examples in a directory. So these are available in the webinar's zip file. So you can follow the links in the second slide and find this. But essentially, when you unzip this file, there will be a directory called standalone MPI. So all examples are for MPI parallel codes. There is an image data example, so that writes into a Cartesian mesh, and then there's an example in an unstructured data directory that writes into an unstructured mesh, into an unstructured grid file. And so these examples, you essentially, with the libraries installed, you go into those directories and then you compile the examples by running make, and then you run them. So when you run them, there are some things you need to, at least one thing that you need to pass to the simulation code at runtime. So before I show what you pass exactly to the simulation code, let me quickly talk about instrumenting the simulation code. So in the examples, both the ParaView source code examples and in my own examples, all files have exactly the same names, so that you can navigate them easily. So in those examples, the main loop of the simulation is called fe driver .c. So it's a C example. There are also some C++ examples in the preview source code. And then there's file fe data structures.c. So they define the simulation data. There is Catalyst adapter, and this is the file where you actually describe your data using this convid node approach. And then there is the Catalyst pipeline, which is the visualization script that I'm going to talk about in the next slide. So when you modify the Catalyst adapter.h file, there are various descriptors that you pass as convid nodes. So it's once you look at the examples, it becomes fairly obvious. But basically, you pass the strings to the library that describe whether how exactly a loading Catalyst, which runtime library for Catalyst, let's say Paraview, you are using. And then there are things like Catalyst script name, Catalyst pipelines, information about time steps or times, simulation times. Channels are essentially the variable names that you pass, and so on. So you describe the data, you describe the three-dimensional arrays with these strings, and then you run the simulation passing the name of the visualization file. So the visualization script that comes with Purview or with Catalyst is actually very basic. I just showed here in its entirety on this slide, and it doesn't do much. So for the example in Purview source code, it simply just print some information about the bounds and essentially the range of the data, and it's not particularly interesting. So what you need to do, you want to replace this default Catalyst script with your own visualization script. And so you do this in Paraview, typically in Paraview just by loading Paraview GUI. And then so you load your representative data set. So by representative data set, I mean a data set which is very similar to how you structure your data inside the simulation code, but now it's written into a file. So where do you get a representative data set? That's another question. So I'll answer that in a minute. But the pipeline is the following. So you start Paraview just on your computer, you load a representative data set, and you create a visualization in the GUI. Then you apply the extractor. So in Paraview, you can go to the menu, and then you will see there will be a number of extractors. One of them is called image extractor, typically into a PNG file. The other one is a data extractor, where you can select any object in your visualization pipeline in Paraview, and then save it save the data from this image as an extractor. And then next step, you go to File, Save Catalyst State to save your script. So that will give you a Python file. And then you will need to, optionally, you can modify your Python file. So essentially, you have to give the attributes names, and these names have to match whatever names you pass right here in the convid node for the variable names. So the problem here is, where do you get a representative data set? So you can create a representative data set from scratch if you know the type and the shape of arrays that you're going to pass in memory to the Catalyst library, but it's kind of a tedious process, and sometimes it's difficult. So in a Catalyst 1, so in the previous iteration of Catalyst, there was a routine greetwriter.py Python script, and I know that it was under development in Catalyst 2, but I don't see it in the most recent version of Catalyst, and I don't know what happened to it. So the way you can create a representative data set is by following an example in Paraview examples. So in this specific file, there is example which simply, if you modify your code in a similar way that is defined in this example, then when you write your simulation data, and so this is your compile simulation code, and you pass the flag dash output and then the file format into which you want to save your data set, then it will save your data set. So I'm not providing more details here. So you can find, if you watch the webinar from 2.5 years ago, you will see I demo an example there. But the idea is that you can actually write a representative data set right from your simulation code. So once you have the representative data set, well, you load it into Paraview just locally on your machine. You apply filters to create exactly the visualization that you like. Apply extractors, either data or image extractors. And then you go to File, Save Catalyst State, save it as a Python script. then you make sure that you modify the name of inside the script, you'll find what is called the registration name. So it's the name of the variable that has to match whatever variable name or names you use inside the simulation code when you're describing your data to convey. And then you run the simulation, right? So here's your visualization script that you just created, and then you run your data, and so this is your runtime, right? So you run your large simulation, and then in one of the in the data set subdirectory, you will find your numerical data set or your data, right? That you visualize with the script. So everything really depends on whatever you were doing in this script, and that was captured through this pipeline. So there is also what is called Preview Live. And in Preview Live, the idea is that you can connect to a currently running simulation and then steer the simulation live. So typically, you will start Preview on your own computer, on your laptop, and then you will have a specially instrumented simulation code that connects to the Preview library. And I also have a demo inside in the webinar 2.5 years ago. So the idea is that once you start running your simulation will connect to your Preview application running on your computer. And then on your computer, you can actually modify the simulation in runtime. You can visualize things in runtime. And I find that it's really an interesting idea, but it's not really, it's so interesting for, it's not so useful for running production codes, but more useful for debugging your simulations, right? So if you have any problems, then you can actually run the simulation and debug its data in memory without saving these files into, well, without saving this data into files on disk. So again, more details on this in the webinar that I did 2.5 years ago. And then if you have any questions, just send me an email and I'll be more than happy to answer these questions. So I saw there was some scrolling link to the webinar presentation. Great. Yep. Yes. So the webinar presentation is so you can find the webinar presentation is linked from the second slide, and I guess you already found. Oops. Let's see, how do I go back to the second slide right here? So on the second slide, there are links to the exact websites. And then you can also find these. So if you go to our training.westgi.ca website, and you can go to tools and let's say visualization or data management. So under these, so here you can search for in situ visualization. So under these, you can find all the webinars that I refer here. So next, let me go to distributed data sets. So if you try to put a large data file under Git version control, you will run into a problem. And of course, the problem is that Git was never designed for storing very large files. So Git was designed for storing text-based data, right? So simulation code primarily, but also, articles, markdown files, so basically text files. So when you try to put a large binary file into a Git version control, what will happen is that you will effectively immediately double the size of your repository, because there is a copy of this binary file inside your working directory, but also a copy of this file inside the Git object store, right? And that is the problem, because now if I try to store large files, maybe we modify large files, so every new copy of a large binary file. So here I'm talking about binary files, so data sets, not text-based files. Every time you modify your binary data set, most likely what will happen, it will change not just a single line, but because there are no lines in the binary file, but it will just rewrite, store the second copy of this binary file, and basically, the size of your repository will grow very, very quickly. So poor man's solution to this problem is it actually works, but I don't really recommend it, but it works. So you can put the repository on a drive which is separate from the working directory. So the idea is that you have a working directory somewhere on, let's say your laptop, and then you have an external drive onto which you put the .git directory. And then when you run Git commands, there is a flag that you pass to Git that will simply tell you that the repository is sitting on a separate drive, right? So the idea here is that instead of storing, 2 copies of the file on the same drive on your, let's say, your laptop, you have 1 copy on your laptop and then another copy on an external drive. And that way you have an automatic backup, and you're not storing things redundantly on the same drive. But of course, if you modify or delete a large binary file, you still have a problem. A copy of this file will still remain in the repository, wasting space. So of course, you can rebase the repository, do things, but it's really a lot of manual work really to, to solve, to give you a very poor solution. So there are multiple what I call proper solutions, but there are multiple software projects that address this problem. So here I list the four main ones. So Git Annex, Git LFS stands for large file support, DataLab, and DVC. So we give webinars on the first on three of them. So on Git Annex, DataLab, and DVC. DataLab and DVC really give you a lot of additional features to track data origin, provision input, and control output when running workflows. So with DataLab or DVC, you can do things like, let's say you are inside a repository, and then you're trying to process some data, and you run the pipeline, and DVC or DataLab will automatically figure that the input data is missing, so we'll actually go and fetch this data from a remote repository. And then once you finish processing, you have new data files, the result, and then it will automatically place the resulting files under version control, things like this. So Git Annex and Git LFS both work really well for this. So they're much simpler tools than DataLab or DVC. So in fact, for example, with DataLab, when you run DataLab underneath, often you run Git, not really underneath, you run yourself by hand, very often Git Annex commands. But I find that Git Annex itself is really a fantastic tool for distributed file storage. So if you look at the difference between Git Annex and Git LFS, they're different by design. So Git Annex uses symlinks, whereas LFS uses pointer files. Git Annex is fully distributed in the sense that there's no central repository, so it can handle multiple backends. So you can have repositories that are sitting on a local file system, on external drives that are mostly offline, on a secure copy or SSH remote files, files that are sitting in Amazon S3 cloud, et cetera, et cetera. So it offers really, really excellent support for remote backends and for offline storage as well. But a big problem with Git Annex is that it does not have GitHub and GitLab support. So it turns a lot of people, away from this tool. So personally, I don't use GitHub or GitLab for storing large files. So I think my problem is I have a lot of drives or a lot of file systems, a lot of remote servers, and I just want to have organize my storage over this large collection of remote files. So Git LFS supports GitHub, GitLab, but big downside of Git LFS is that it relies on a centralized server or centralized remote that has that has to keep track of where all the files are, right? So all updates are always synced, must be synced with the centralized server, which is, in my opinion, a downside of Git LFS. Anyway, so my specific use case is, as I mentioned, is I have a lot of files, and then I have a lot of external hard drives or SSDs, or maybe some remote servers on which I want to keep a subset of the files as well. Let's say, I don't know, project file system inside or on a cluster, right? So some of my data files on a project file system, on multiple clusters on their project file systems, and I want to have a good way to to easily search this data. So I want to have the ability to keep everything organized. So by that I mean any folder structure. So I don't want Git Annex or any other tool to tell me exactly how I should organize my data. And I want to sync all these data sets. So they must be searchable even when offline. So if I have data on an external hard drive, I don't want to mount this hard drive to know that my file is there. I want to be able to find it without having to mount this drive. And then I want to have a multiple backup copies. So at least a single backup copy of everything. And then for more important files, I want to have multiple and remote backups as well. So, due to its distributed nature, I much prefer Git Annex over Git LSF, but everybody's needs are different, right? So some people might find that Git LSF just suits their needs much better. So how does much time I have? Okay. So how does Git Annex works? Well, it is based on is built on top of Git. So underneath, you can actually run a lot of Git commands, but Git Annex tries to automate this for you. So I will actually show a demo. So the only demo in today's presentation. So here I'm going to create a new directory called webinar. And then I'm going to cd into this directory. And then here I'm going to, so I have an alias. Instead of running Git Annex command, I will write I will just say GA, so that simplifies typing. And then similar to Git, all Git annex commands are followed by a verb, right? So you do things like GA init, GA add, GA sync, status, and so on. So as you can see, very, very similar to the original Git commands. So let me create a directory. I'm just going to call it earth. And then I'm going to cd into the directory. And then I will initialize a new Git project. So that created the familiar .git file. And then I'm going to initialize a new Git annex project in this directory. So I'm going to say GA Git annex init, and then earth, the name of the local repository or the local annex, right? So if you work with multiple annexes, then it's very useful to refer to them by the names that you give with git annex init command. So now if I do ls, not a lot has changed, but if you drill down into the structure of the Git files, you will see that there are some additional objects that were created when I ran this git init, git annex init command. So here I have a function that creates, it doesn't really matter what this function looks like, but basically the idea is that it creates a number of large random binary files. So when I say populate, let's say 10, it will create 10 files, and these files are, they're fairly large. They range from 1 to 33 megabytes, I think, in size. So they're fairly large. So it created these, 10 completely random binary files. And then now, if I want to add these files to Git Annex control, so instead of running git add, I'm running git annex add. So I'm going to say git annex add and just add all these files to Git Annex control. So what happens, three things happen underneath when I run git annex add. So first of all, it moves the files to this object store subdirectory. So under git annex, there is objects folder. So if I check in there, git annex objects, you will see that here I have a bunch of subdirectories, and inside these directories I have my large files. So it moved all my large files into these subdirectories, and then in the original working directory, it actually replaced the files with symbolic links with exactly the same names. And so now the next step is these links we are going to be added, and then git annex add also added this link to the staging area, right? So similar to running git add, now these files were added to the staging area. So in fact, if I run git status, you will see that there are a bunch of new files that were added to the staging area, and these files need to be committed. So you could run at this point git commit, but if you are inside an git annex directory, actually strongly recommend not to run git commit, simply because it will just mess up your mind and you will be making mistakes. If you're running both git and git annex commands. So what I suggest to do in this case, you can run the command git sync, and it will commit those symbolic links to the Git repository. So now I have the symbolic links. So as far as Git is concerned, everything is in sync now. So these links that you see here, they were committed to the Git repository, right? But these files are actually pointing to Git Annex object files that are stored somewhere inside the .git directory. So now when you run Git Annex sync, right? So instead of running git commit, I run git annex sync. Underneath, it also does three things. So first of all, it commits all new local links. So underneath, it runs git commit with some generic message. Then it will update the current repository with all changes to its remote. So right now, we don't have any remote, so it doesn't do this step. But if there were some changes to remotes, it will actually go and fetch those changes from the remotes that are currently online, right? Which I mentioned that I really like Git Annex for being able to work with offline files, right? So that means that it will only be able to fetch information from the remotes that have previously uploaded its information before. And then it will go and push any changes from the current repository to all its remotes, if any have been created. So underneath, Git Annex uses branches to communicate to offline and online remotes. So if a remote is currently offline, that it will create a new branch and will place the outgoing information into the branch. So the next time when remote comes online, you actually be able to download this information from a branch instead of going to the to the main repository. So the system, the way it's the communication is organized between online and offline a repository is really fantastic. I really admire the programmers who did it. So it makes it really easy to work with remote files. So at any point you can run, as you saw, you can run Git status, or better Git Annex status, to check on the status of the files. And in this case, it doesn't show anything because everything now is in sync. So the changes have been pushed into the repository. There's also command git annex varies that shows you the exactly on which drive each file is stored. So in this case, we initialize 10 files, and all the files are stored inside the Earth annex. So now, if you go to a different annex, you can add files there, and then you will see that. So if here I'm talking about remotes, you can add files, and then whenever you push things in a repository, you run command git annex sync. All changes will be propagated, will be stored locally, as well as propagate to any repository that happens to be online at the time. So, and this makes it very easy to propagate changes and well, actually, let me show you. Let me give you a demo. So here, what I'm going to do is I will create a new repository that I'm going to call, Venus. Let me create that directory. So now I'm going to go in there, and then I'm going to start a new repository. So actually, let me do it via a clone. So that is easier, because that way I don't have to merge completely unrelated histories. So here I have my Earth repository, and then I'm going to say, actually, yeah, let's create a Venus directory. And then I'm going to go into Venus, going to say git clone, and then I'm going to clone the Earth annex into, clone. Oh, yeah, I forgot to create the annex directory. Okay, well, I'm cloning just Earth. Okay, right, and then, oh, yeah. As always with live demos, always make mistakes. But here the idea is that now I have this annex, and then if I do get varies, it shows that the files, get annex varies, it shows that all the files are on Earth. So now if I add, let's say, 5 new files, so here I added 5 new files, I'm gonna add these files to the annex. So let's add all test files to the annex. So currently, as you can see, if I run g status, it'll show me that there are 5 new files, and then I run the sync command. So now with the sync command, if I run git annex where is, it will tell me where each file is sitting. So there are 10 files on the Earth drive on the Earth annex, and then there are 5 files on the Venus annex. So now if I go back to the Earth annex, so it's right here, yeah. And then if I run the same command, now it will show only 5 files, because we have not synced things yet. So now let me sync things. And now, as you can see, after synchronization, the Earth annex knows that there are files both on Earth annex and on Venus annex. So here is the, instead of using the git annex command, so it's not an alias in my case, I actually use a function. And here I coded some additional functionality. So I wrote a allocate verb, which will give me just much nicer formatting for files. So it just gives me a single output line for each file. So you can see that I have 10 files on Earth, and then I have 5 files on Venus annex. Anyway, so synchronizing these repositories, undoing things, removing files from annex control, removing multiple files or directories, working with remotes. So all these things are really easy. And so again, please go to the webinar that I gave on Git Annex that was about 6 months ago. And there I ran a lot of examples live. So to summarize, one thing that I found very difficult for me cognitively was this clash between commands git and git annex. So whenever I want to run a git annex command, often by mistake, I run the git command. And I found what really helps is just replace the git annex command with something that is sufficiently different. So in my case, just having an alias or function ge actually worked really well. So git annex works really well with SSH remote. So for example, you can place some files on a cluster file system. The only thing that I have to worry about is whenever you're running syncing, and it will go through all remotes, and it will try to access an offline remote, and then it will try to secure copy some information to or from the remote, and that can be slow. So a lot of people complain about this, but it's actually really, really easy to solve this problem. Is if you don't want to communicate to a SSH remote, you can simply disable it, right? So you can do things like enable it only when needed, and then disable it after that, and there is no harm whatsoever. So remote is just a tag which you can turn on and off. So I don't have a lot of time, but I still have one more topic to cover. And let me just quickly talk about it. So the last topic is tar. So as you know, we always request that people do not store a lot of files on parallel file systems, because parallel file systems, well, they just were not designed to handle millions and millions of files. So the standard solution is please take all your small files and pack them into tar archives. But tar has its limitations. So tar was originally introduced to Unix in January 1979. So it's almost 50 years old now. And the main limitation, there are quite a few, but the main limitation is that it doesn't have a built-in index, right? So it was designed for a sequential write to a tape, and it does not have a built-in index that tells you exactly where each file is sitting. So that makes it really, really slow to search for files inside a tar archive and to extract files as well, because tar will have to start scanning the archive until it reads the header of the file that I'm searching for, and then it will extract that file, right? So searching for things inside tar archives and extracting things inside tar archives is very slow. There are some other limitations as well, things like padding and a few others, but there's a tool that is called DAR. So instead of tape archiver, now I have a disk archiver, and I gave a webinar on it about 6 years ago, I think. But I still actively maintain it. Still works really, really well. So it's open source, and originally it was designed in 2002. So the funny thing, it exists exactly for half the time that tar existed, right? So tar is 46 years old. And DAR is 23 years old. But it was designed to essentially address all these limitations of tar, right? So it supports, first of all, it has an index, right? So at the end of each DAR file, you have an index. You can do full differential incremental backups. It has built-in encryption, has built-in error compression, lots and lots of really nice features. And it's available on the clusters. You can also install it on your own computer using your favorite package manager. But basically, the way you use is you pass a few flags. So here, how is you create a tar archive? So you say, you create an archive all.tar, putting everything into it from the test directory. So with DAR, you run something similar. So you're creating an archive, and in this case, you're creating an archive called all. So it's going to have slices all .1 .dar, all .2 .tar, and so on. And then -g means that you're putting everything under test into the DAR file. So when you're creating DAR archives and you benchmark it, you will see that the time is going to be essentially the same. Well, for DAR, it's actually a little bit longer because it needs to create an index as well. But extracting, this is where DAR really wins, right? So here I did a benchmark on an external hard drive attached to my laptop. And see, here I have from a 17 gigabyte archive. So if I extract from a tar file, a random file somewhere in the middle, it takes about 8 seconds. When I do this for a random file somewhere in the middle, it just takes half a second with DAR. So this just shows you how much faster extracting, searching for things with DAR is, right? So it's really great for random file access, unlike tar. So if you have a lot of files, then I really, really highly recommend to look into DAR storage. So whenever you create the archive, essentially you pass a name to the archive, right? So here I'm saying that please create an archive called all right here. So underneath, what it will do, it will create a bunch of files. So with that name, so in this case, I'm creating an archive called Monday. And then you will have the slice name, which is just a number starting from 1, 1, 2, 3, and so on. And then there is the usual .dar extension. So here is just an example of how you can create differential archives, right? So first, I create an archive called Monday that includes all the files from the test directory. So here I create this archive right here. And then here I'm just showing you how to restore a file or how to restore a full directory. And then let's say on Tuesday, I made some modifications to my files. So now I have a new, let's see what I do. I create a new random file, and then I create a new differential backup, right? So backup is going to be called Tuesday. And then it's a differential in reference. It's referencing Monday as a previously created full archive. And then on Wednesday, I yet another make some modifications to the file. So I erase one file, and then I add two new files, and then I create a new Wednesday archive, and so on. So in this case, I will end up with at least three files, right? So it will be a file for Monday one.da, and then there's going to be Tuesday one.da and Wednesday one.da, and then to actually extract them, you can simply go in reverse order. So if you want to have a full restore from all backups, then you'll have to go in restore order. So first you restore Monday, restore Tuesday, restore Wednesday. But if you can also look into files, into indexes, and then if some file was added some midway, let's say on Wednesday or on Tuesday, then you can actually restore just from a single differential backup. So anyway, really, really high recommend DAR. Works really fantastically well. It's very easy to limit the size of each file. So if you know that you'll be writing this to an external drive with some quarter or some finer size, then you can limit the slice of each DAR archive. Very easy with a little bit of scripting to limit the number of files per each slice inside DAR. As I said, encryption is built in, which is fantastic because you can securely store your data on, let's say, a shared file system. Really, really strongly recommend this tool. So over the years, I dealt with a couple of tickets where people ran into problems with DAR, and in each case, the problem was that they didn't finish. They didn't wait for DAR to finish, so they started the DAR command, and then they just went somewhere else and didn't monitor. So make sure that whenever you're creating DAR archives, your DAR finish is running, right? Because the archive is added, sorry, the index in the archive is added at the very end of the DAR command. So that means that if for some reason your file system went down, then your DAR command will die, and you will not have the backup, the archive that you are trying to create. But yeah, just basically exercise common sense. So monitor DAR as it runs. So make sure that there are no errors. That file systems, for example, don't go offline in the middle of creating an archive. And then you can read the index, check the index. So if the index is fine, then the file should be fine as well. So I assume you're not running into quota issues, have read-write permissions, etc. So if you monitor all these basic things, then DAR should work really well for you.